Thank you. So before I move to the next topic, let me just put something about the scaling. Just to remind you that we are taking space derivatives to have dimension 1, time derivatives to have dimension z. Z is the dynamical exponent. And then this means temperature and chemical potential. We'll also have this dimension z. Then energy density and pressure have dimension d plus z minus theta. Theta is the hyperscaling violating coefficient. The entropy density will be d minus theta. And remember, this is like the effective number of space dimensions. And then there are other quantities. So from the thermodynamic relation between energy, pressure, entropy, and charge density, one deduces that the charge density has dimension d minus theta as well. Then from the conservation of the charge, no, this should have the same scaling. Then one finds that the current has dimension d minus theta plus z minus 1. And then the gauge potential should have the same dimension as the chemical potential, the time component, and the space component the same as the space derivatives. And from here you get that the electric field should have dimension z plus 1, and the magnetic field should have dimension 2. So then you can use Ohm's law. This will be the current, this is the electric field, and this is the conductivity. And then the conductivity has dimension d minus theta minus 2. Okay, so I will use this a bit later. So I will just leave it up there. So now I'm going to talk about systems at finite density and temperature. So in the gravity side, I'm going to think about charged black holes. And then in the field theory side, we're going to identify this with some metal if we want to do some application to condensed matter. Okay, so a very rough classification of metals could be this one. There are metals that you can describe with Landau's theory of the Fermi liquid. And then there is anything else, which is you cannot describe with this theory. Okay? And this is usually called non-Fermi liquid, which is a bit of a misnomer because it's still made of fermions, or a strange metal. Okay, these are just names. So this in condensed matter appears in some materials. I think the place where it's more clear is something called heavy fermions. So you have, in these heavy fermions, you have some metal, and then this metal has some magnetic impurities. Okay. So this means you put some atoms in the metal which carry a spin. These are not part of the original, if you want, lattice you had of atoms. And then you put them, many of them, and they form some lattice of magnetic impurities. This is called also the Kondo lattice. And this spin interacts with the electrons in the metal. And there are two things that can happen. You can have that the impurity interacts with some electron with the Kondo coupling, and this produces some kind of bound state. So this will be some Kondo effect. But it can also happen that this impurity interacts with some electron, and this electron interacts with another impurity. And this produces an effective interaction between the two impurities. And this effective interaction could be antiferromagnet, for instance, or ferromagnetic. So we will like to order the spins of this impurity and form an antiferromagnetic or ferromagnetic state. And there is a competition between these two. No? Here, you are screening the spin of the impurity, and here, you want to form some magnetic order state. So by the way, this gives a renormalization to the mass of the electrons, and the effective mass of the quasi-particles you have is much larger than the mass of the electrons, and that is why they are called heavy fermions. So you have a competition between the two, so the Kondo and the magnetic order. And in between, there is a quantum critical point. Okay? And then if you add temperature, then you have the quantum critical region. So if you measure the properties of the metal in this region, they are different from the ones that are predicted by Landau's Fermi liquid theory. So this is an example of a strange metal. Sorry? Say it again. Yes, this could be the density of impurities. Well, I think you can tune this interaction by pressure. Yeah, you can. Yes, so you can tune these interactions with pressure or other parameters. So. Yes, yes. Also, if you change you can tune these interactions. You can also change between the two situations. So I don't remember now exactly what were you tuning? Well, because here you have a screen spin, so you don't see the spin of the impurity anymore, and here you have a magnetic order. So they have different symmetry realizations. So, okay. Now there are other materials where you also see strange metal behavior, like high TC superconductors. Although it's not clear there is a quantum critical point there. But the point is they are not understood using this ordinary Landau Fermi liquid. So in order to explain the difference, let me say a few things about the Landau Fermi liquid. So we start with gas of fermions. So this means they are free or almost free. Let's say we have a gas of free electrons. We can neglect the interactions. They are non-relativistic electrons, so they have an energy which depends on the space momentum as k squared over 2 over the mass. This is the dispersion relation. So if you start adding electrons to this system, you can just put, because they are fermions, they cannot occupy the same state, so you can just put one of them for each element of volume of the phase space in units of h bar. So this means the total number of fermions will be the volume of the system times the integral over momentum in units of h bar from 0 to some maximum value of momentum. No? So as you increase k, you increase the energy. So first you occupy the states of lower energy, and then you start adding more and more electrons, and then you are filling some volume in momentum space. So you have, this is momentum space. You have some kind of a sphere of radius kf. This is the Fermi sphere, and the surface is the Fermi surface. So this is at 0 temperature. This means that the occupation number is, as a function of the energy, is just a step function. Where this mu is the energy at the surface of the Fermi sphere. Okay, if you are at finite temperature, then you should change this by the Fermi Dirac distribution, which you all know. So exponential of epsilon minus mu over t plus 1. Okay, so this won't be like a sharp surface, but there will be some exponential decay. Okay, now imagine you want to excite a little bit this state. You can add, for instance, send some light to it that will be absorbed by some electron. And then you can make some electron change its momentum. Okay, so because all these states are occupied, if the change in momentum is small, then it cannot be in directions parallel to the Fermi surface because these states are occupied. So it can only go in a direction transverse to the Fermi surface, no? By some change in momentum q. So the energy of this excitation will be like the energy at the Fermi surface plus, let's say Q is this, well, the other will be this distance. Then you're adding Q in the same direction. And then you can expand if this Q is much smaller than Kf. So this will be epsilon. So you get something linear in Q, and this is the derivative with respect to Kf, and this is the Fermi velocity. So effectively, for excitations of a small energy, you can expand the wave function of the electron taking out some phase factor, which oscillates very fast, which is proportional to the Fermi energy, and then you have some wave function which oscillates more slowly, depending on the difference with respect to the energy at the Fermi surface. And then effectively, this means that you can approximate the action for the fermions by an action that looks like this in momentum. Okay, so you'll have the time derivative, and then this will be the kinetic term. So this looks like a relativistic fermion. It has a linear dispersion relation, and the propagator will be something. We'll have a pole like this. No? Or in general, you can also write it in this form. Okay, where I have reintroduced the chemical potential and the dispersion relation. Okay, so now, in principle, you can use the fact that you have this Fermi distribution, the fermions are free, and so on, to compute thermodynamic quantities and transport quantities in this theory. But you can get the same results if you use scaling arguments. So what is the idea? Here, the electron cannot move in the directions parallel to the Fermi surface, only can change momentum in the direction orthogonal. This means that the effective dimension of this theory is one special dimension, no? That agrees with this kind of effective action I wrote. No? Or in our language, this means the hyperscaling violating coefficient is d minus 1. On the other hand, it looks like a relativistic dispersion relation. So if I rescale momentum to preserve the dispersion relation, I have to rescale frequency in the same way. So this means the dynamical exponent is equal to 1. Now you can use those formulas I have there. So you just see that temperature and chemical potential have just dimension 1. Energy density and pressure have dimension 2. Entropy has dimension 1. And then conductivity has dimension -1. Well, since the pressure has dimension 2, it means that at low temperatures, I can expand it like the Wilson coefficient times the chemical potential square, another coefficient times chemical potential times temperature, another coefficient times temperature square, so on. The entropy is the variation of the pressure with respect to temperature. So in principle, there could be a constant term, and then let me divide this by 2. A linear term, and then the specific heat, which is proportional to the derivative of the entropy with respect to the temperature, will be just linear in the temperature. Okay, so this is the result for a Fermi liquid described by Landau's theory. Well, so far we are only doing the free gas. Okay, now from here, okay, now you should do a calculation, and then you will see that this coefficient is not there. Okay, this coefficient will break charge conjugation. So in fact, you find that the temperature is proportional to the entropy over this other coefficient, C2. And this will be the variation of the energy with respect to the entropy. And you can integrate this equation. This will give you some constant plus 1 over 2 C2, the entropy squared. And then if you use this formula again with this coefficient equal to 0, then you find that the energy density is a constant plus something that goes like the temperature square. Okay, so the specific heat is linear in T, and the energy density minus the vacuum part is proportional to T squared. The fermions have a non-relativistic dispersion relation, but if you're looking at excitations close to the Fermi surface, then the effective theory is relativist. It has a relativistic dispersion relation. So the RG flow takes you to a theory that lives on the Fermi surface, which you can think of as taking patches on the surface. Right, it's like you have many copies of a 2D system. The Fermi surface effectively looks like that. Well, this part looks conformal, but there will be corrections that break conformal invariance. But okay, so that's regarding thermodynamics. Let's talk about transport. So the typical description of transport in a metal is the Drude model. Okay, so we said we have a gas of free fermions. So these free fermions just move to the metal without doing anything. And then sometimes they find some impurity or some lattice defect, and then they can scatter through it. And then they travel again without doing anything, and then they scatter again, and so on. So because of these impurities, they suffer some drag. And then you can describe this using a simple equation. So the force acting, suppose I introduce an electric field to make the electrons move. So the force the electrons suffer is proportional to the charge times the electric field you introduce, and then there is some dragging term. Okay? And this tau is the scattering time, which is the typical time between two of these scattering events. So you can solve this equation. It looks something like this. This is the momentum at time equals 0. So you see that there are some exponentially suppressed terms. And when the time is very large with respect to compared with the scattering time, then the momentum just becomes a constant. So when t goes to infinity, the momentum is just something proportional to the electric field. And then from here, the velocity is just the momentum divided by the mass. And then the current density you have is just the charge times the density times the velocity. And that gives you the famous Drude formula. Okay. And well, people usually, this will be the conductivity. In condensed matter, people usually talk about the resistivity, which is the inverse, which will go like it will depend on the scattering time, like the inverse. So we can estimate this resistivity at low temperatures, at least the temperature dependence, just by using the fact that the average velocity will be something like 2 over m, the energy over the number of particles. And then this will have a contribution which is the energy at 0 temperature. And as we saw, the correction to the energy is proportional to T squared. So there will be some coefficient times T squared. Sorry, and this is the velocity square. Okay, so then you can plug. Okay, so the other ingredient is that the average time is proportional. Sorry, the scattering time is proportional to the distance between these impurities, which we can call lambda, over the mean velocity, which is the time. This will be the time it takes go from one to the next. So putting these two things together and expanding at low temperatures, one finds some constant part, and then there is a contribution which is proportional to T squared. If you expand, if you introduce this formula, this is proportional to the mean velocity. And then if you take the square root and expand at low temperatures, you just get that the leading contribution goes like T squared. Okay, so then in the Landau Fermi liquid, the resistivity grows like T squared at low temperatures. So this and these are the behaviors. Okay, so all this was for the Fermi gas. Now, the idea of Landau is that you start with a Fermi gas, and now you turn on a small interaction between the fermions. Okay, that will make this energy, which was k squared over 2m, change to some different energy, which depends on the coupling now. So it gets some renormalization. But then you can think that the new eigenstates of the system are still fermions. They are like dress electrons. So they still carry the same charge and the same spin. It's just their energies are slightly different to the ones of the free gas. So you can think of your new states as fermionic quasiparticles. And these fermionic quasiparticles are weakly interacting. So you can treat them as a Fermi gas again. So you have some Fermi gas of quasiparticles. So then everything that you use for the Fermi gas, for the free Fermi gas, applies when you turn on a small interaction. And then you repeat this, you keep increasing the interaction in an adiabatic way. And if there are no phase transitions, then you always stay in the same universality class where you have a free gas of quasi-particles. So all these results, the result of the resistivity and the specific heat, are the same, even if the interactions between the electrons are very strong, because the interactions between the quasi-particles are weak. And in this case, this propagator also gets modified. There is some renormalization. So now this energy is not the one of the free electrons, k squared over 2m, but it has the same form with a pole. And the residue also changes. This residue is between 0 and 1. And then, well, if you're at 0 temperature and you look to the distribution, the occupation number of fermions, then as a function of energy, then you have a step function for free fermions. This residue is telling you that there is still a jump, but now it gets reduced somehow. So this separation is determined by Z. Okay? So you still have a sharp Fermi surface with some jump, but now this deviates from the step function, the occupation number. Okay, and this is due to the interactions. Okay, so if you measure resistivity and it doesn't behave like this at low temperatures, then you cannot explain it with the lambda Fermi theory. Yeah. Yes. No, I use that the effective values of the theta and c for the theory at the Fermi surface are these ones. No? And that fixes the scaling. They depend in the sense that I fix them, and then I got this scale, these powers. Theta is the number of space dimensions minus 1 for the theory on the Fermi surface. It's universal for the Landau Fermi liquid. So, yeah. Yeah. Yeah, good question. So the point is there is the density here. So the density also has dimensions. And then if you check, it has the right dimensions. Okay. So, okay, so you can think of modifying this a little bit if you have some self-energy corrections. No? And then the behavior of the system is going to depend on how these self-energy corrections behave at low frequencies. So assume that at low frequencies this goes like a power law. Then if this alpha is larger than 1, the exponent here, then this term is much smaller than the linear term at low frequencies. So then you still have something that looks like a quasi-particle pole. So essentially it will look similar to a Fermi liquid. If this is smaller than 1, then this term will dominate at low frequencies. And usually this is a complex quantity, so this will give you some pole which is in the complex plane, and typically it won't look like a quasi-particle pole. So you will lose this picture of the free gas of quasi-particles. No? That case will be, this will be a Fermi liquid. And this will be a non-Fermi liquid. And then there is the marginal case, where this sigma of omega will be actually omega log omega. Okay, this still dominates, so there is no Fermi liquid. This is called the marginal Fermi liquid. Well, it's because this term will dominate. There will be some singularity, sorry. There will be some singularity at the Fermi surface, but this will be some kind of branch cut rather than a pole. So it will be a branch cut, or it will be, depending on what this is, some complex singularity in, away from the real axis. So, yeah. Yeah, all this you have to think about collective modes, right? So it will mean just that before you have a collective excitation, would look like a wave that was propagating for a relatively long time before decaying. Now it doesn't look anything like that. It's just something that doesn't look like a well-defined wave. But yeah, you still have a Fermi surface because there is still a zero in this denominator. Okay, even though it doesn't look like the one for the Fermi gas. Okay. So in the examples I was, in the heavy fermions, for instance, or in the cuprates, the high-TC superconductors, they find that the resistivity is linear in the temperature. And then there are other quantities which have also some exotic scaling. But other things like the specific heat looks like the one in the Fermi liquid. So part of the difficulty of describing these strange metals is that some quantities look like the Fermi liquid and some other quantities look different. So maybe there's not a single way to describe all the properties of the strange metal. Okay. So let me try to explain how one can describe a strange metal in holography. Maybe I can start. Okay. So as I said before, a metal will correspond to some charged black hole. And then the simple thing we can think of is Reissner-Nostrom. So you have an action, which is just Maxwell coupled to gravity. And then you have a cosmological constant, so you have ADS. Okay, so I allow here some parameter Q that you can tune these parameters, so if Q is very large, then you can treat the gauge field in a probe approximation which sometimes is useful. Yeah. Yeah. Well, the idea is you construct a toy model that has the properties of a metal. Let's say uh, it has non-zero conductivity, and it has finite density and temperature. And then you look that it has some scaling properties. And these scaling properties will determine the dependence on temperature of the resistivity and things like that. So this will look like some kind of a strange metal. You don't know if it corresponds to a condensed matter system, but it gives you a way to compute, for instance, here this marginal Fermi liquid was kind of postulated in a condensed matter model. No? You just cook up some action, and then you add a term in this effective action such that it will look like this. So it's some effective theory. No, I don't think well, you can get this from some effective theory that you write and you compute the Feynman diagram that gives you this, but you don't deduce this from the microscopic theory. So it's a toy model in that sense. So, right, so here is, I'm picking some Hamiltonian also that I can describe using the holographic dual, and I compute correlators and things like that. And this is simpler, actually, than computing Feynman diagrams. So then I can compare. Well, the idea is in these systems, you have some kind of a scaling invariance. They are strongly coupled or strongly correlated. And yeah, I'm saying there is some scaling of some quantities. No, no. This is not adding more symmetry. It's because it's different. It's a local symmetry, so you don't see it. No, but the only symmetries that matter are the ones that correspond to the boundary of ABS, which are the same. No, I'm not. You have against. No, it's like the ordinary ADS-CFT. You have a gauge theory, which without gravity. Okay, and yeah, but forget about the strings. No, but we are talking about symmetries, and this theory doesn't have gravity, and then you describe it with a gravity dual, which has the diffeomorphisms, as you are saying. And these diffeomorphisms, you don't see them because they are just a local description. No. No, I'm not saying that. Yeah. Mm-hmm. Yeah. Yeah, yeah. Okay, maybe let me continue, and then you will see. Yes, maybe it will be more clear if I continue. But let's say this action has a solution, which is Reisner Nostrum. So in general dimensions, it looks like this. RH is the position of the horizon. N is the mass, which is related to the energy. Q is the charge. And then you have a gauge field. Okay, so this is the solution. Now there is a chemical potential. This term here tells you there is a charge density. And you can compute the temperature and the charge density, the entropy, and so on. So let me just give you the formulas. Will be RH over 4 pi L squared times D minus 2 Q squared. This will be the temperature. Now you see that there is a value of Q for which the temperature is 0. This critical value is square root of D over D minus 2 in this coordinates. And then you have a black hole with some horizon, but has 0 temperature. So it corresponds to the extremal case. So there are interesting things that happen in this extremal case. So let's expand the black hole factor close to the horizon in this extremal limit, and it will look something like this. Okay, so usually, if you are at finite temperature, this factor has a single 0. So the exponent here is 1. But in the extremal case, it has a double 0. So this makes the horizon of the extremal black hole to have very special properties. Let's change the coordinates. So introduce, I expand for R equals RH plus some small epsilon parameter. And I have this new radial coordinate zeta. And I also rescale time by the small parameter. And this L2 square is given by the radius of anti-de Sitter with some factor. Now, if you plug this in that metric and take the limit where epsilon to 0, epsilon is going to 0, to leading order, then you find that your metric becomes something that looks like this. Okay. So this part is ADS2 in Poincare coordinates. And this part is just has a constant factor in front and is just flat. So the effective metric is ADS2 times R to the D minus 1. I'm using D for the space-time directions, D capital D for the space-time directions. Okay, so what will be the interpretation of this thing? Well, the usual interpretation is that for every point in the RD minus 1, you have a conformal field theory, in quotes, in 0 plus 1 dimensions, so only time direction. Okay, so this will be like the ADS2 is dual to some CFT in 0 plus 1. And this is something that people identify with local quantum criticality. So roughly speaking, this will mean that the degrees of freedom that become critical are localized in space. For instance, you could have impurities localized in space, and there is a critical point for these degrees of freedom. And then it will look something like this. One can also identify this geometry with a Lipschitz geometry where Z is taken to infinity. No? So space doesn't scale, but time does. And well, the easiest way to see it is you start with the Lipschitz metric. Then you redefine your radial coordinate with this 1 over Z, and you rescale time and space. With the Z. And then if you do that, the metric becomes just something that has an ADS factor, ADS2 factor, and then something that looks like this. So when you take Z to infinity, this becomes a constant, and then you recover the ADS2 RD minus 1 metric. So, okay. So another interesting point is that the gauge field has this form with some, it goes like 1 over Z with some electric flux there. And then yeah, the entropy is like 2 pi this electric flux times the charge density. You can, if you look at the formulas for the entropy and the charge density, you can deduce this relation. And this means this electric flux is given by the derivative of the entropy with respect to the density. Okay, so this is fixed by this thermodynamic derivative, entropy over density. Okay, so what are the properties of this point? Let me see the time. Plenty of time. So we're going to compute some correlator to see how things look. First, let's do some scalar correlator, which is the simplest thing. So the action for the scalar, we are going to take it to be dd plus 1 x square root of minus g gmn dn phi dn phi, and then a mass term. So this mass determines the dimension of the dual scalar operator through this formula. Yes, I'm going to compute a correlator, so I'm going just to do small fluctuations of this scalar. So it's going to be just fluctuations around the background. So also this means that it's just linearized fluctuations, so it's also enough just to keep the mass term. You could have a more complicated potential, but for linear fluctuations, higher order terms don't matter. No, because the scalar field is not turned on. And then you just do linear fluctuations around the background to see what is the spectrum, if you want. So this covariant derivative is defined with some charge for the scalar. Okay. So now you do small fluctuations. So you can write the linearized equations of motion. And then if you work a little bit, then at 0 temperature, the equation looks like this. Well, first, I'm going to expand in plane waves. I can do that because I have a translation invariance along the directions of the boundary. So there's going to be some field which depends on frequency and momentum and the radial coordinate. So let me write the equation. And I'm just looking in the near horizon region where I have the ADS2 geometry. So then the equation looks like this. Okay. So let's first look what happens if we approach the boundary of the ADS2 space. This is when Z goes to 0. And this will be going away from the horizon. No? At some point, this will match with the rest of the Reisner-Nostrom geometry. So if you look there, then you can ignore this term. This is suppressed in this limit. And then you are kept with this second derivative term and this term here. So this looks like the equation of a massive scalar in ADS2. Okay, and the effective mass in units of the ADS2 radius, L2 squared, will be the original mass in units of the original radius times this electric flux squared. And then you can have some contribution from momentum. And there is a contribution from actually the square of this term. So you see that if you're at 0 momentum, just for simplicity, you see that you get a negative contribution to the mass. Okay, so in principle, this could make this scalar field unstable in the ADS2 region. The effective dimension, if we think of ADS2 dual to a CFT, then the effective dimension in this CFT will be given by this formula, where the mass enters in here. And you see that in general, it will be momentum dependent. So this will be a function of momentum. So okay, so if you expand this scalar field close to the boundary, it will look something like set to the 1 minus delta effective. Okay. Plus set to the delta effective of K. Okay. This is the usual non-normalizable and normalizable modes. Now, what we want to know is what is the relative coefficient between these two modes. Okay? Because this relative coefficient usually tell us what is the correlation function of the dual operator in the infrared, this G of omega K. Okay. So if we know this relative coefficient, this will be like knowing the correlator in the infrared theory, in the one where you have a CFT in 0+1 dimensions, of some operator that lives in this theory and is dual to this scalar field close to the horizon. Okay, that won't be the full correlator in the full theory. The full correlator in the full theory, let me call this Carly J, will be something like this. If we talk about the retarded correlator, so it will be some, if you do a low frequency expansion, there will be some frequency dependent terms here. There will be this contribution. And then there will be some coefficients here that depend on the expansion. And then there is another term in the denominator. Okay, so this comes from taking this solution that lives in the ADS2 region and then extending it extend it to the region where you have the full Reisner-Nostrom geometry. No? You will have some solutions that are solutions to the equation of motion in this full geometry, and then you have to match to the near horizon. And then, because this is asymptotically ADS, then you can compute the correlators in the usual way. And what you find in the end, that this matching procedure will give you that the full correlator in the dual field theory contains this infrared correlator, but it's not just proportional to it, but it enters in this more or less complicated way. Okay, but all this comes from some low frequency expansion, are analytic powers, and all the relevant dynamical information is in the infrared theory. So we will look at this guy. So in order to compute this coefficient, you need these two are independent solutions of the equations of motion. So you need to impose some physical condition on the solution to fix the coefficient. And this condition is put at the horizon. So we are going to be interested in computing the retarded correlator. Okay? And this will fix the boundary condition we have to put at the horizon. So if we look at the opposite limit, this is the horizon in ADS2, then one can see that one can expand the solutions in plane waves with some extra powers. Sorry, this will be set. Okay, so I'm calling this in and this out because the time dependence of the solution goes like minus I omega t. So this means that as I'm approaching the horizon, the time grows to keep the phase constant for this solution. So this solution is ingoing in the horizon. And the opposite happens for this one. This one is outgoing. Okay, so the physical condition is that if you introduce some energy in the bulk, it will fall inside the black hole if you let it evolve in time. So that corresponds to having the ingoing solution. And this will be the time reverse process. So if you want to compute the retarded correlator that corresponds to advance in time, then you have to keep this solution and make this one 0. Okay? So this fixes your solution in the horizon. When you go close to the boundary of ADS2 and expand, it will have this form, but now this coefficient is fixed. And the form of this coefficient is roughly some function of the momentum times the frequency times 2 delta effective of k minus 1. Okay, so this is what you expect if you have a conformal theory in 0+1 dimensions, this power law behavior. No, the thing that is different from what we are used to is that now this dimension depends on the momentum because of this local quantum critical behavior. And well, the retarded correlator in time will look like a power law as well. Okay, so a couple of words about the this thing that this mass could become negative is that in ADS2, you get the -1 because you're doing the Fourier transform with respect to time of the correlator. So if you compute the time-dependent correlator, it will go like tau to the -2 delta, and then the Fourier transform gives omega to the delta -1. Yeah. Yeah. Yeah, so it's like for every momentum, you have a different operator. So it's like, because you have this local behavior, then suddenly you have an operator for every momentum. So ideally, you want to maybe compactify and then have a discrete spectrum of operators. Right. Here, the space directions appear like the internal space in the usual holographic constructions. So it's like instead of having the S5, you have R2 some power. So then the momentum are the Kaluza-Klein modes in this space. Okay, so there is something called the BF bound, Breit-Lerner-Friedman, that Horacio talked about, which is the lowest mass you can have for a field without it becoming unstable. And in ADS2, this will be for the effective mass in units of the ADS2 radius. This will be larger or equal to -1/4. And then this gives a bound on the mass in the units of the original ADS, which will be greater or equal than this thing. Okay, so this is like the BF bound in d dimensions, and then you get this extra contribution from the charge. Okay, so if you have a charge field, then it means that for the system to be stable, you need the mass to be above the naive BF bound. In terms of the dimension, this means the dimension in the ultraviolet theory should be greater or equal than something that depends on the charge as well. So in particular, there is a situation where if this charge of the scalar is larger than 1/4 times this flux, this you can check by looking at the metric and finding what is this, then there is no relevant deformation. So delta is smaller than d, that will satisfy this bound. So there will be, this scalar field will be below the BF bound in the ADS region. And this will be interesting for tomorrow. Okay, so this is one thing. The other thing is some spectral asymmetry. So you can compute at finite temperature, what I said. You can compute all this at finite temperature. You just have to add a black body factor here. So you'll have some minus f of z. And this f is something like 1 minus z over zh. and then the gauge field is multiplied by the same factor. So this will be the same ADS2, but a small temperature. Okay, so it's slightly away from the extremal limit. And then the retarded correlator can be computed exactly. Let me skip the exact formula, but if you Fourier transform it, it will look something like this. So this will be the effective dimension. I'm talking about the one that lives in the infrared, no? So in the ADS2 region. Okay, so there is this factor that appears here and tells you there is an asymmetry between positive time and negative time. If you look in frequency, it means that the correlator is not symmetric with respect to frequency equals to 0. No? The correlators we saw before were all symmetric because there was time reversal invariance. But in this case, it won't be, and then this spectral asymmetry is determined by this flux here. So you can also see this as having some value of the frequency around which you can find asymmetric correlator, which is in fact the product of retarded and advanced. And this frequency is proportional to the temperature times this flux. And then this is related to the thermodynamic derivative that I wrote before. Right? It's proportional to the derivative of entropy with the density. So actually, the fact that this spectral asymmetry is proportional to this thermodynamic derivative through this formula was also found in condensed matter systems. So in some condensed matter systems that you can describe as essentially impurities or a quantum mechanical model of interacting fermions, then you find that the spectral asymmetry is given by this thermodynamic derivative in the same way as in ADS2. Okay. So this was regarding the scalars. One can also compute the correlator of fermions in a similar way. Let me check the time. Okay. Yep. 10 minutes. Thanks. So now the action we will be using is the action of free fermion. So this will be the Dirac matrices in the ADS spacetime. And then we have a master. And then this covariant derivative acting on the fermion now contains not only the gauge field with some charge, but also the spin connection, because now in ADS this thing is non-zero. Now this will be tangent space indices and these space-time indices. So you can compute the correlator for the fermion in the same way as we did for the scalar. You find the linearized equations of motion, you solve them, you impose the ingoing boundary condition at the horizon, And then you expand close to the ADS2 boundary to see what is the correlator from the relative coefficient between the normalizable and non-normalizable mode. If you look at the expansion close to the boundary, you see that the effective dimension of this field also gets some momentum dependence. And the correlator, the full correlator, no, after you do the matching to the asymptotic region from the near horizon region, looks like this at low frequencies. Okay. So these quantities are evaluated at k equals kf. We are expanding around some kf that you obtain from the calculation. Okay, technically, it's a bit involved, so I'm not going to show it, but this is what you find. And then here you recognize that this is the contribution from the infrared theory, right? It looks the same as in the scalar case, but with the effective dimension for the fermions. So now, this is very similar to the thing we were commenting at the beginning. No? If you have that this effective dimension is larger than 1, then you find that there is a pole which takes this form. No? I'm expanding now. Okay, so there is this gamma coefficient here. So this looks like a linear dispersion relation, and then there is some correction by some higher power. Okay, so this looks like the typical behavior on the Fermi surface. Now, if this effective dimension is smaller than 1, then the solution for the frequency is something like this. Okay, so this looks nothing like a propagating degree of freedom. There is some branch cut, and then there is no good quasi-particle. The residue, this residue also vanishes at the Fermi surface in this case. And it stays constant in this case. So that looks very much like a non-Fermi liquid. And then you also have the marginal case when delta F equals 1. Then, okay, there are some complications because we will have logarithmic terms in the expansions I was showing. And then in the end, it happens that this term becomes omega log omega. Okay, so that corresponds to the marginal Fermi liquid. So then, in this model of the Reissner-Nordström, close to the extremal solution, so very small temperatures, you find that these fermionic correlators behave like non-Fermi liquids or marginal Fermi liquid, depending on the momentum and this mass. And then you also got that this spectral asymmetry behaves like in the condensed matter system. How much time? 3 minutes? Okay, so let me just make one more comment that is in condensed matter, there is something called the Latinger theorem. Which just says that the total charge equals to the sum of different species of fermions times the charge of this species times the volume of the Fermi surface, of the Fermi sphere for each of the species. Okay. Now, in this ADS2, in this extremal black hole, you find that, well, there are no fermions in the bulk. You can find solutions where you have some non-zero profile for the fermions, then they will have some Fermi surface. And then those Fermi surfaces in the bulk satisfy this kind of relation. But in general, you find that this is modified by something which is the electric flux at the horizon, plus the sum of whatever Fermi surfaces you have. So the Fermi spheres. Okay. So then, okay. In condensed matter, this will be true. Here we have this extra term. Now, the usual interpretation people is giving, and usually this comes from Sachdev, is that there is also a Fermi surface in this in the field theory dual to this extremal black hole, but is made out of degrees of freedom that have some color charge. So you don't see them directly in the bulk. So then this is goes by the name of fractionalized Fermi liquid. And this word of fractionalized is inspired by some models of, for instance, fractional quantum Hall effect, where your quasi-particles carry a fraction of the charge of the electron, these collective modes. But of course, all observables will be given by things that are in integer units of the charge of the electron. So here is that the single trace operators are the observables, and then these color degrees of freedom are like the fractional quasi-particles, and then they can form a Fermi surface. And the idea is, although there is no proof, the idea is that this contribution from the electric flux of the horizon comes from this Fermi sphere of the fractionalized degrees of freedom. Okay, I will stop there.